Okay. Okay. So, uh, hello everyone. Good evening, and welcome to today's research salon. And today I'm going to present a paper titled DEF8 Mobile IoT Communication Exploiting Stealthy Speaker-to-Gyroscope Channel. And this paper is from Dr. Quayden's group. So if anyone remembered, I have presented another paper in many months ago, that is gyroscope steal your information, and this paper is still a follow-up work published in the MobiCom 2020s. So let's get started. Here is the outline today. So at first, I will give you the introduction and some background knowledge and of the gyroscope and the mathematical model. And then I will show you the system design and finally the evaluation, and we can conclude this paper. Okay, so here is the introduction. So we're now embracing the era of the Internet of Things, the IoT. The IoT can connect various applications intelligently for people's convenience. So we have various standards such as Wi-Fi, Bluetooth, and LoRa, and these standards are proposed to help build this everything-related network. So because they're using different protocols, they are actually some scenario specific, and sometimes we can only use one of them because we need some specific peripherals on one device. So here the problem arises. Well, let's first look at this example focusing on the robot communications. So the first issue is the robots Wally and Eve, they adopt different wireless protocols. For the Wally, he used Zigbee and the low energy Bluetooth. But for this robot, she's using Wi-Fi. So there's no communication link between them, and so they cannot transfer information. And similar failures happens when if there is some electronic mechanic field is blocked out. So there's no way to use EM wave for communication, and that's why we always need to build new wireless communication technology, and that should be cheap and robust. So in this paper, the author focuses on the micro-electromechanical system, that is MEMS, and it has been reported that the MEMS system can generate readings when there is ultrasonic ultrasound signal impinging on these chips. So if the frequency range is properly selected, the ultrasound signal will fall into the bandwidth of interest. So this MEMS system will give us a reading with no contact to establish a non-contact communication method without any other peripherals. And another reason is such system, for example, the gyroscope accelerometer, are now become indispensable. So you can find it anywhere on your inside your VR set, the wearable devices, and inside your smartphones. So how the author used these gyrophones to build the communication system? Apart from that, they also introduce us very interesting application scenario. So here is the story. The spy A wants to send the some security data to the spy B, and in this case, the spy A used a smartphone or a speaker to generate some ultrasound, which is cannot be cannot be heard by the human. The SPY-B will use all these possible devices equipped with gyroscope. For example, the smartphone, the wearable devices, or some robots. He will use the gyroscope readings to decode the signal from the SPY-A. So this channel can be regarded as stealthy, and people always believe that the gyroscope is not that sensitive. So the SPY-A and SPY-B will steal your information and talk secretly. And here is the contribution for this paper. First, they investigate a stealthy speaker-to-gyroscope channel without restriction of peripherals, contact, fixed placement, and so on. And they also analyze the relationship among axes in a gyroscope under resonance. And the third contribution is they develop a robust communicating system for a mobile IoT network. So here is all for the introduction. Let's move to the background and the model. Here is a structure of a standard gyroscope. The concept of the gyroscope structure is detailed showing in this figure. You can see there are some driving springs and some frames, mass, anchors, and fingers. We can see there are multiple axes, the x-axis, y-axis, and for some gyroscopes, they also have z-axis. On each of these axes, when there is an accelerations, the spring will be driven by the Coriolis force. So driven by this force, the spring will generate a single degree of freedom vibration along the axis. So it will change the capacity between these fingers and anchors. So the capacity changes, it will influence the voltage or the current inside that MEMS system. So they will give us different readings, indicating that there is some acceleration along that axis. So the overall process inside this gyroscope structure is as follows. First, they will arc has the acceleration data, and it should be multidimensional. After that, they use some amplifier to amplify this analog data, and filtering process is afterwards to remove the higher frequency components and noise, and only keep the low frequency parts. And finally, there is an analog to digital conversion. So it will give us direct digitized readings from this gyroscope. And let's shed some light on the spring system. This mechanical system has a natural frequency centered at here, denoted as Fn. So when the system is vibrating at this natural frequencies, it will give us the biggest magnitude response. We call it is resonance. And if we're looking at the first figure, we'll see that when, just like I said, it will give us the biggest response at the natural frequency. And there is a 3 dB bandwidth can be shown in the subfigure A. And for the subfigure B, we can also know that the ratio between the working and the natural frequency will also affect the signal phase. So here is the background of resonance spring system, and the gyroscopes are inevitably different because they're using different springs. They are only there are not only different among the types of the gyro model. even use a same gyro model, it will there's a significant discrepancy even when you're using the same gyro models. So you can see from this figure, all this colored line shows the resonant frequency range for not only the starting and ending frequencies, but also the bandwidth of all the gyro models are different. So we can say the popular gyroscopes have a narrow resonant frequency range, and all of them are above the human audibility. So this kind of communication is actually inaudible from the human beings. So they did some feasibility investigation, just like I said. It shows the inaudibility. That is, the frequency range is above the human's hearings, and such kind of communication system needs no peripherals. They only need commercial speakers for the transmitter, or if you're using a hi-fi speakers, for example, 32 bits with 384 kilohertz something rates will cover the bandwidth of interest without any other peripherals, and they have little interference. Calls for other ultrasound applications, such as some material inspections, they prefer the bandwidth above the 40 kilohertz. So they always work on some higher frequencies, which will not affect what we want to use for communication. And here is a mathematical model behind the relationship between the gyro readings with the ultrasound. So let's say the speaker will generate a sinusoid signal, and this sinusoid signal will impinge the chips of the MEMS system on one axis, and here is the Crowley's force with some amplitude and some phase. We can see the response of this force will still be the sinusoid signal with the same frequency, but different amplitude and additional phase shift. So it's still another sinusoid signal. And after that, we will feed this signal to an amplifier and filter. This amplifier and filter will introduce some additional gains and phase shifts, but will not affect the frequency if the amplifier, we assume that will be linear. And the third thing is the AD conversion with a match sampling rate. Because the working frequency for this sinusoid signal from the speaker is usually several kilohertz, but for the gyroscope, the sampling rate can be only a few hundreds hertz. For example, 200 hertz for a standard gyroscope. We know that it's is insufficient if we are using Nyquist low band filter and low band sampling. But we can see, because this is a very narrow band signal, we can then adopt the Nyquist passband sampling, and this frequent impulse in the frequency domain will fall into the n fold of the Nyquist sampling region, and at last, in the digital frequency domain, it will end up at the frequency of f1. So at the reading, the user will know that the response signal will have an unknown amplitude, some unknown phases, but a frequency which is related to the transmitted frequency. So here is a mathematical model for this system. So far it seems perfect, because we can now encode and decode the information. However, it still remains some problems. So what else should we do to make this system work, or what the problem is still need to be fixed? Then we can move to the system design section. So the most serious problem is described as unpredictable deviation of output frequency. This is because the gyroscope itself is not designed for other purpose. The sampling rate of the gyroscope frequency is not always stable. So on the left in the red box, it shows the desired signal after such kind of processing. And on the right, if we slightly change the frequency, sampling frequency fs to fs plus some delta fs, it significantly changed the frequency at the readings from the f1 to f2, because the f0 is much smaller than fs or fs plus delta fs, so it will show a remarkable offset. And this observation is made in this subfigure. In the green circle, the desired frequency is 107, but with this predictable sampling drift, we can still see an offset f2 equals to 61 Hertz in the red circle. So, but we still notice that the trajectory, if we use a scatter plot to plot all the points on the x-axis and y-axis, that means we show this trajectory on the XY domain. We can find that this trajectory looks like an ellipse. So it means although the sampling drift occurs, but the frequency of the sinusoid signal in the x-axis and the y-axis is actually the same. So we can conclude it as this sample rate drift occurs simultaneously on each axis. So we can use this property to eliminate the unknown impact from the sampling rate drift. So here is the.
Could you go to previous one?
Okay.
Slide. So this equation is more like empirical, right?
Yeah, it's a curve fitting.
So that's always the case, or it's based on their, experimental setting?
I think we did some experiments, and this is the readings in their experiments. So you see, you have so many scatter plots like this, and they just fit this curve and say that yes, it's just like ellipse. So that is the case. So although we know that for the amplitude and the phase, it's unknown, but since it shows like this, we can still conclude that the frequency is at least the frequency is the same. So they want to use this inter-axis properties to eliminate the unknown sample rate drift.
So the x-axis is what is the amplitude? Y-axis is phase shift, right? Or is
no. They are all the actually they are all the readings, because for this gyroscope they have 3 axes.
Oh, okay, x, y. Okay.
Spatially, yeah.
Okay.
They have X, Y, and even for some they have X, Y, Z. Yeah. So in some they show the X or Y plane, and it show like this. So That is.
So there is no outlier based on their experiment. It's kind of a perfect.
It has outlier here.
It has outlier.
Yeah, we can. If, for example, here is the outlier. Yeah, because it's still noisy signal. It should have some outlier.
I saw the blue dot. They represent the raw data. Okay, the blue dot. That's an outlier. Okay, that's okay. The red line means the raw data fitting curve. Okay. Oh. All right then, but yeah, it's not that convincing. But anyway, yeah. Thank you.
Oh, okay. So let's move on to this solutions. So as I just mentioned, they possess these properties. So we can the straightforward solution is to apply a multiplier and a mean filter. So what is the meaning of applying a multiplier is simply to multiply the x-axis reading with y-axis reading. So it works like a mixer. Since it has the same frequencies, it will generate a very low frequency component. Actually, it's perfectly working. It is a DC component, but for this part, because the frequency part adds up, it will generate a higher frequency. Although we do not know the exact frequency in the for this signal, but what we can know is after a low pass filtering, this part will be removed, and if it runs perfectly, we'll only have this DC components, suggesting the useful signal we want to transmit. So that is very straightforward. And after solving this problem, we can finally describe the design as this following parts. The depth aids, that is the name of their system, have 4 parts, and 1 receiver identification, 1 encoding, and 1 noise reduction. And then last, there is threshold and decoding parts. So that's all these 4 consists of this their system design. And it can be they're all straightforward and reliable. So we can briefly introduce all these parts. For example, the receiver identification. This is based on the different gyroscopes have various resonant ranges. So it works like a fingerprint. For all the receivers, we can say that because they have 3 axis springs. They will have, if one string is one string's resonant frequency overlap with another strings, we can use that for the communication. So because they are all different, the transmitter can send a chirp signal, and the chirp signal's bandwidth can be specified as one of these receivers, and the target the true target will receive the full range signal from the starting point of the band of interest to the end of the band of interest. So that is called receiver identification. And for the encoding, they're adopting pulse interval encoding. That is just the use of non-coherent modulation. That is the pulse modulation. The pulse interval encoding just use the interval between 2 rising edges to indicate the bit 1 or bit 0. For the bit 1, it may be the interval will be narrower, but for the 0, the interval will be longer. So it is used for the encoding. For the noise reduction, they're using some average filtering after multiplication. So for the noise, it's basically have some higher frequency components which can be filtered out after the multiplication. And in this paper, they also mentioned the noise induced by the transceiver movement, but it can also be if the scale is large, they need to they use adaptive threshold. But if the scale is small, it can be regarded as noise, and this noise can still be separated after some domain transfer or using some empirical mode decomposition. And anyway, it's separatable, so it can be removed sufficiently from the useful signal. And at last, the threshold and decoding. They are using a maximum entropy threshold method to derive the optimal threshold. So for the amplitude beyond that threshold, they can marked as pulse incoming and use this PIE decoding to reconstruct the signal from the transmitter. And here is the example. The transmitter uses a speaker to transmit all the modulated pulse via an ultrasound. So here you can see it is the 1001 with different intervals. And at the inside that gyroscope will give us the reading, analog reading like this. So it is from only one axis, so it'd be vulnerable from the random sample rate drift. So we can combine the two dependent axes will give us a combined channel, and here is the threshold showing in this line, and the information can be successfully reconstructed using PIE decoding. So just like I said, the movement can still be filtered out, so no problem for the noise removal. So here is overall story for the system design. And finally, we can move to the evaluation. So at first, they give us some fixed parameters. For example, the sampling rate is fixed at 200 Hertz. So don't be surprised. Don't be surprised with this number, because for the gyroscope, it deals with low frequency signals, so the sampling rate is actually really small. And the distance they test their performance, test their bit error performance is 15 centimeters, and the pulse width using here is 15 milliseconds, and we transmit the signal using the power smaller than 5 watts.
Oh,
and
sorry for jumping. So could you tell us, what's the lower bound for the transmission power?
The lower bound, actually,
they use how much power?
Okay, so I think the sentence is actually because they're using different kinds of transmitters, so the transmitter power varies, but they're no more than 5 watts.
Let me change the question a little bit. So for the transmission power, do they use the power more than 1 watts?
I think so, because it cannot be. I think what they are trying to say is that they are using some proper or some power is suitable for the experiment, but no more than 5 watts, means they are very close to 5 watts.
Yeah,
but they cannot be uniformed. Yeah.
I believe you can guess the reason why I asked this question, right? So you do the system implementation. I believe you have a perfect understanding how much power Wi-Fi is using, how much power, for example, 5G is using, right? Could you tell everybody how much power, for example, your Wi-Fi 5G phone is using? Transmission power only.
Yeah, so the yeah, point two if for receiving something like that.
According to the 3GPP standard, is less than 1 power, right?
Yeah, it cannot be.
I don't know. I really doubt the motivation for this paper. Why you use so much power to do the transformation for such a very short distance? And I don't know, why don't you use some Wi-Fi? I don't think any device, if they don't have Wi-Fi access, I don't think they have the gyroscope, sensors inside as well. Did you see any kind of devices, for example, they have gyroscope, they don't have Wi-Fi access?
Actually, I think they're considering some scenarios that they are for example, the robots. They need the gyroscope for navigation, but they definitely have some wireless peripherals, but one may use some other standards, so they cannot communicate with each other.
Why?
One use Wi-Fi, one use LoRa, they cannot.
Why we want to use that? Why? Is there any specific scenario or applications you can point out? For this one, I definitely is going to use the gyroscope for communication. I cannot use Wi-Fi or any kind of a mature wireless transmission technologies. With much lower transmission power, with much higher accuracy, with much more mature decryption protocols for security.
Okay, so I have the same feeling like this, but I think it's still reasonable to say that because just inside their paper title, that means a stealthy channel. So although they did not mention the security concern as they do in their last paper, the accelerometer, steal your information one, but it's still some to try to use some not very sensitive sensors to transmit the information. So I believe this is the case. And for some scenarios, just like they said, we're always welcome for new technologies.
So stealthy channel is just a term, right? I believe the stealthy channel, what they mean is just a secure channel. But if you want to guarantee a secure channel, I believe Dr. Yuan is an expert, many students, they're security people as well. There are multiple ways. And we have much more mature techniques. Why you want to propose this? And you have so much power consumption with so short distance and so low transmission data rate. If you use the pulse encoding, I believe you're physically a guy, you know that. If you use the pulse encoding, the transmission data rate is very slow. You know that, right?
Yeah, especially for this narrowband system.
Exactly. I don't know why the wireless technology developed up to date. Well, it makes me want to laugh. They never ever considered the motivation for this paper. There must be certain kind of motivation.
Actually,
we didn't figure out or we didn't dig it out. Otherwise, if they only motivate the paper like in this way, I don't know, we probably don't need to consider all the complicated protocols they design. Motivations wise, I don't know why they want to propose this.
Yeah, so the stealthy channel part or some novel wireless communication technology.
I don't think the stealthy channel part is a selling point. The stealthy channel is just like I said, just a term. It's just another way to say, oh, I want to transmit the information securely.
Yeah, I think, and also they say there's mobile IoT, so maybe all these transceivers are some robots which can move around.
For all those mobile IoT devices, can you name anything they have gyroscope, but they don't have Wi-Fi mode or Wi-Fi components in there? Can you name anything? Even for the iRobot I have in my house, it has Wi-Fi access. It has a gyroscope that, yeah, that's true. But it also has Wi-Fi access. Right?
Yeah. Yeah. Yeah, I agree, because
and also you don't want to control your iRobot within 15 centimeters, use the gyroscope. You want to control wherever in your house. For example, you have a very big house, then you can use your phone to control your iRobot to do the clean work at any corner of your house. Right? It's much, much longer than 15 centimeters.
True. That is true. Yeah.
So, but I think you present 2 gyroscope papers by now. Have you ever doubted their motivations?
Yeah. For the last one, I think that do make sense. For this one, I just think they're using the same technology but change of scenario. Instead of stealing your voice, your voice information, they are trying to use some man-made communication signals for other uses. Yeah.
I don't buy it. I know you're working on some magnetic induction together with Debin, right? Well, before Debin graduation. So you know why magnetic induction never fly? It can only be used in a special scenario for underwater environment or underground environment. You know why? Because
the range.
better technology there in the air, right? So they never fly. Even they can transmit probably, I don't know, probably within 10 meters or 3 meters, 4 meters in the air, much longer than this one, but they never fly. They can only be used for recharging, but they cannot. Well, people don't use that it's for communications in the air. They use that for communications underground, underwater, for specific environment requirements, right? Where the degradation is very high in the underwater environment, also the complex components for the underground environments. So the propagation degradation is very high, right? They have a reason to use that. But for this one, I don't find a single reason to use this new proposed technology.
Okay.
Again, I don't want to. I appreciate you guys, pick up some top conference paper, you read this paper, understanding this technology and design there. But you never ever forget, right? Don't get lost in those fancy technologies. You need to think about, do you think this one is useful or not? That's the most important things. I mean, all the researchers and engineers we should do. I mean, that's the first thing we should consider. I don't mean for this paper, I want to, put on some negative comments on there. It doesn't matter anyway, it's published in MobiCom, right? But we just want to know, if you do this kind of complicated design, for what?
Yes, the thing is another sound vibration side channel paper, so it kind of interesting. Yeah.
But even for that scenario, do you think there's a kind of alternative solution? Which one probably is better than this one?
Yeah, you can use the microphone to receive that signal, definitely. That's true. I think, it's still hard to propose something new and make it work.
There is many things in the world, in nature, you can try to discover or whatever. But if you have very good solution, why you want to go for the inferior solution? If there's no specific reason for that.
Yeah, it may. That's true.
So, yeah, I think the power consumption is at the high level. Probably one reason is that so here they use the acoustic signal. So definitely, if they can use the Wi-Fi, the side channel, they will occupy the radio spectrum. So that's a radio spectrum. So how to say? So it will cause interference to other device or others, because nowadays like 2.4 and 5 gigahertz is already a crowd. So a lot of people now said so don't want to let other application to occupy this spectrum. But here they use the acoustic, so probably so they will not cause interference to the radio signal. I'm not sure. I think probably this one reason, but still, so its transmission power is too high. So
yeah, I think that's kind of an argument, but
yeah.
Honestly, I don't buy that much, because for example, if you can consider some say channel congestion scenario, for example, we're in the stadium or we're in the whatever, we will watch a sports game or something, right? There's a lot of people staying there. Yeah, probably your Wi-Fi is used up, but if you use this one for 15 centimeters transmission, who you want to talk with? that's
There are a lot of
yeah, not a problem.
There are a lot of articles even from the InfoComm and MobiCom, like so. I think that like the detection or the transmission range is only just like within half meter, but these articles are still being accepted by this top conference. Sometimes it's probably the review just focus on the technology, the new technology things, so they did not see its real world application.
Exactly. I think ultrasound, it can have much better applications. For example, I think all of you guys know that we use that in the medical, right? So to detect the asthma, right? So you use ultrasound and use Wi-Fi signal to do that. I think that makes sense, right? That's really makes sense. But for this one, I don't know. I just doubt their motivation anyway. Okay, Chenpei, I don't want to, embarrass you. I just want to say you keep in mind for any paper you read, that's the first thing you need to consider. Okay. Even for paper.
Okay. I got you.
Okay, please move on. Thank you.
Dr. Pan, maybe I can add something up. So this power issue, reminds me about federated learning defense the malicious clients. I'm thinking about whether we can ask the clients to report the power consumption to the federated learning server. And then at the server side, we can build like a power consumption model, because the server understand the transmission distance between the client and the server. And the server also know, because the client will register the system, like the hardware with the server. Then if there are some malicious clients trying to do like data poisoning or model poisoning, probably the power consumption will be a little bit different from those benign clients. Then if we can use such like a side channel detection, we probably can find out any malicious clients trying to attack the model.
Yeah, that's possible. But like you said, all the clients, they self-report their power consumption, right?
Right.
You mean at the same time, we do certain kind of monitoring, we do some side channel information, say we have another party to monitor, say how each client is doing how much power, something like that.
We can do some monitoring, but also we can rely on the reports, because the malicious clients do not know what other clients will how much power they will consume, because the malicious clients don't know the transmission distance of other clients, don't know the operating system, the computation power.
Well, but I think the malicious clients, they can be on it for probably several rounds, they can estimate the distance between themselves and the server, right? So they're going to know how much power for transmission to the server.
Mm-hmm.
They can also do self-estimation. Say if I running ResNet 20 or something, certain kind of data set locally, how much energy I'm going to consume. If I got all this information and I lie, I mean, for the first few rounds, I can be honest, but for the later, rounds, I just go ahead to lie. Then how can you detect that?
Yeah, that's an interesting question. Yes.
Yeah, I think as long as we rely on the self-report consumption, we don't have a very good way to detect that.
But any other like wireless or side channel metrics we can leverage at the server side. So maybe we can combine the client reports, and also we do some monitoring from the server side.
Like I said, if you're close to the client, to the malicious client, you can monitor the power leakage. I think in wireless communication community, we have because whatever wireless transmission is based on the power, right? We can monitor the energy and power leakage. I mean, in very old days, there are people talking about that, but the condition is, and the assumption is you need to be very kind of close to the malicious client. But if you consider the federal learning scenario, the client can be everywhere. That assumption, I mean, that condition cannot be satisfied, honestly. So yeah, I think it's very challenging from only wireless point of view to detect those malicious ones. Yeah.
Yeah. Okay.
Yeah.
Okay, I got it.
Probably
Okay, thank you.
Some other way, yeah, some other way.
Yeah.
All right.
Yeah. Okay. Yeah, Chenpei, maybe you can continue.
Yeah, you can continue. I'm sorry. Yeah.
Thank you. So let's move on, and I'll keep I'll keep the rest of them quickly. So for the second evaluation, they rotate the speaker around the gyroscope. So it just fix the receiver and rotate the transmitter in the XY domain plane and showing this figure. Because for other planes, they are quite similar. And this figure can reflect the placement of gyroscopes, makes no difference. And conversely, if we fix the transmitter, the speaker, and rotate the gyroscope because of it shows some directionality. So we can see in this figure the effectiveness of the range is in 22.5 opening angle of the speakers with beta error rate less than 0.1% at 15 centimeters and 1% at the 20 centimeters. So here is the orientation.
For this one, I also have another question. Could you go to the previous one?
Okay.
We all know that the ultrasound, because they're kind of very focused, right? So kind of like a beamformer. They have direction. But if you like what you show here, I mean the range actually is pretty wide. It's from negative 30 to almost positive 30, right? So for example, if the two receiver, they're kind of close to each other. I think you mentioned this kind of a receiver identification somewhere, but just in case, two receivers, they're close to each other, right? So can both receivers, they can get a signal, or only identified, the I would say designate receiver will get a signal?
Yeah. The receiver identification is to transmit a chirp signal before the data transmission. So this is basically based on the bandwidth differences between devices. For example, for device A, it uses up frequency range from for example, from they're using a range from 30 to 50, and the other use up 50 to 70. They're totally different. So that's before transmission. The transmitter will transmit a chirp. So the receiver will listen to this chirp and identify which is the target receiver. If this chirp covers the whole range of the band, it is the target. Otherwise, it is not.
The chirp cover the whole range of the band. What do you mean? For example, if their frequency is for say 40 kilohertz to 70 kilohertz, so the chirp covers the whole spectrum.
Yeah, from 40 to 70. Yeah,
that's the target receiver.
That's correct.
But just in case, say, there is some error or whatever, right? So during the transmission, so is that possible? We never ever can identify the receiver.
Actually,
for example, if the chirp signal only covers say 42 to 70, it's not cover the whole spectrum from 40 to 70. So do we think that's a proper receiver, or it's that's not the receiver I target that?
You mean there exists some errors in the chirp signal?
Yeah.
That depends on the confusion matrix. The high score will assign this signal to the target user. Yeah.
Another question is, I know you mentioned the gyroscope is just like fingerprint. Everybody is unique. I mean, IoT device is unique. But I believe as long as they're from the same manufacturer, they have a lot of overlaps, right? For example, another example exactly relate to what you're doing, the magnetic induction. All the coils, they're different. We can claim that as well. But they have some overlaps. Even for the resonant frequency, they have overlaps, right? So
that's true.
Is there any false positive ratio for the receiver identification?
In their paper, they show a confusion matrix of 16 different kinds of gyroscopes, and the score is quite satisfying.
No, I mean the same type of gyroscope. I know if a different type of gyroscope, they're definitely different. Just like the magnetic induction, if you use a different terms, you resonate at different frequency. That's for sure. But the problem is, if you find a similar gyroscope with the same type, similar, and you stay close to each other. For example, we all have cell phone, right? Our smartphone, they use the same type of gyroscope. If we stand close to each other, can you uniquely identify the target receiver you want or not?
I believe they mentioned that in their paper. They try some different gyroscopes the same the same kind of gyroscopes by different individuals, and they can still perfectly distinguish from each other.
Then what is the magic then?
Actually, I'm not sure.
The physical phenomenon behind. That's what I want to know.
Okay. Yeah, maybe I omit this part. Maybe they mention that. I'm not sure. That really got me.
Yeah, they claim they can uniquely identify the target gyroscope. I doubt that. If they use, I mean, gyroscope is a very common technology. I mean, when I was a panelist at NSF, I saw a proposal. They use a very unique material to control the transmission distance so that you can do the authentication with that specified material design, the transmitter, transducer, I would say. Yeah, that makes sense to me. But for this one, all the gyroscope, they come from the very similar materials, and those materials are not very special. If there is no some reasonable explanation, I really doubt that. I really doubt their claim.
Yeah, this is only an easy method they propose, and they also notice that it's not contradict to some traditional methods such as you adding overhead before the payload. That can be also possible if the first method fails.
But anyway, I think the two questions I asked today, you need to carefully think about that, right? So don't easily trust or believe whatever they claim in their paper. You need to figure out reason why, with very deep understanding.
Yes, I agree with that.
Yeah, think twice, think 3 times, and always keep the, I don't know, the mindset of doubts. Okay, it doesn't matter the paper from top conference, from Nature Science, right? So, no paper is perfect, right? But anyway, yeah. Please continue.
Mm-hmm. Okay, so they also test the communication range by increasing the power to 30 watts. So although it heavily depends on the device they are using, but most of the distance can be extended up to 14 meters with less than 1 bit error rate. So here is some figure showing that. The first one shows different gyroscope chips, and the second figure shows different speakers. And we can always say that if we increase the power, the distance increase, that's for sure. So at last, the transmission capacity is also evaluated. Since this kind of transmission is a binary symmetric channel, so the channel capacity is different from what we are using for the Gaussian sources, Gaussian channel. So for this binary symmetric channel, we can see the channel capacity is showing in this equation, and it's related to the pulse width and the bit error rate. So a shorter pulse width will means more information in a unit time interval, and it can possibly cause more errors. And the channel capacity, well, if you look at this equation, this figure, you can see if we increase the pulse width, and we can see the bit error rate will drop because we are transmitting less information in a unit time interval. But also the capacity will drop since it's related to the pulse width. And for the second figure, the ODR means output bit rate. That is also the sampling rate at the gyroscope. So we can see the channel capacity ascend with the incline of the ODR up to 47.4 BPS. So we can see there is a slight increase in the bit error rate, but it still remains very low level. It is actually smaller than 0.6 percentage. So that means if we increase the sampling rate of the gyroscope, we can actually expect a higher channel capacity. So one thing need to be pointed out is in this experiment, they maintain the product of these two different values at a fixed 0.01. So here is evaluation on the transmission capacity. So in that paper, they also test the motions and some noise detection, but That is not the main story, so I just selectively choose these evaluations. So finally, let's go to the conclusion. And they first probe the relationship among axes in the gyroscope under some resonance. And they use the diversity of resonance frequency range as a fingerprint for the receiver identification. And then last, the performance of the DEF8 can reach up to 47 bit per second with a very low bit error rate, even under the motion interference. So that's all for this paper, and thanks for listening.